So in the last section, we talked about how waves can have matter-like properties, that light can have photon or particle-like properties through the photoelectric effect. And that led us to question as to whether the opposite is true. Can matter behave like waves? In a lot of science fiction shows, we like to show matter behaving like waves, teleporting and those kind of things. So that's an exciting opportunity. If matter can behave like waves, what interesting things can happen? And at the time that Einstein was doing his work, a man by the name of de Broglie came up with a relationship that for matter waves in his relationship here, where the wave-like properties of matter is equal to the proportion right over here. So if I take Planck's constant divided by the momentum of a particle, that would describe the wavelength of matter. And if matter does have wave-like properties, it would follow this equation. So really, if I would calculate my own using my mass and my slow velocity, if I would take that very small number and I divide it by a momentum that humans would actually have, we would find out that our wavelength is incredibly small and wouldn't be consequential. We don't really travel around like waves when objects are really big. But when we get objects that are really, 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 really small and traveling really, really fast, that wavelength starts to approach things as small as 1 times 10 to the minus 10 meters or 1 times 10 to the minus 9 meters. So small particles can technically travel at wavelengths that could diffract or interact with matter. And that was proposed by de Broglie. And thanks to him, we were actually able to design experiments to prove that very small particles like electrons have wave-like properties. So in this first task, we're going to calculate the wavelength of matter using his relationship. Okay, so we're going to try to do this first problem where we're going to calculate the wavelength of an electron that has a speed of 5.5 times 10 to the 6 meters per second. So using de Broglie's equation, where wavelength is equal to Planck's constant divided by the momentum of that particle, which is Planck's constant divided by the mass and the velocity of that particle, we'll get 6.63 times 10 to the minus 34 joule seconds divided by 9.11 times 10 to the minus 31 kilograms multiplied by that velocity. And if I punch that all into my calculator, I should get a wavelength of around 1.32 times 10 to the minus 10 meters. Okay, that's small. Okay, what we know, for example, for light is around, like blue light, what we learned before was 400 times 10 to the minus 9 meters, or 4 times 10 to the minus 7 meters. Okay, so what that means is the wavelength of an electron traveling that speed is much smaller than the wavelength of light. That we can't see it. It doesn't show up, register in our eyes as light. It's very small. It's about the size of a diameter of an atom. Okay, so it would interact with the sizes of atoms, which we're going to learn in another video. And one more practice calculation, we can calculate the wavelength of an electron if they gave us kinetic energy. Okay, so remember, the kinetic energy formula is equal to 1/2 mv squared, and another useful formula for kinetic energy is 1/2 p squared over m. Okay, so in this formula, I can calculate the momentum. If I calculate the momentum using kinetic energy, I can then go back and calculate the wavelength of an electron. Okay, so if I rearrange this formula, okay, that formula becomes 2 times the kinetic energy times m, okay, square rooted will make it, that's my momentum. Okay, so if they gave me the kinetic energy, I can solve the wavelength by taking h over the momentum, which is going to be equal to h over the square root of 2 times the kinetic energy times the mass of an electron. And if I research and I plug these numbers in, what I will find is my answer will be 2.79 times 10 to the minus 11 meters. All right, so here are just two sample calculations of how we can apply de Broglie wavelength or de Broglie wavelength. And once I know the wavelength, I can start treating electrons like waves, and waves can diffract and refract. So we can start using the wavelength to examine the wave-like properties of matter.